welcome everyone to this morning's seminar. I'm pleased to be able to be here today to talk to you about lessons on timber construction and maintenance for modern timber bridges. And it's most of what I'm going to talk about today, after having been in the field for 48 years, is a process of trial and error. And I often think that I've learned more from my mistakes than I have from the stuff I've done right. And so that's what's going to go on today. And who is it that I work for? I work for Wood Research and Development, and they're a IAS certified test lab and third party. And we have a large commercial design division for vertical and horizontal structures. And over the course of my career, as you can see, we've talked about some of the awards. I'm going to zoom through this because there's no sense of hearing that again. But the mass timber today has changed the way we think about timber around the world, in G10 particularly. Back in the day when I started designing glue lam structures with plywood panels and sheathing, we didn't think of it as mass timber. And my tallest building is 12 stories and 535-foot clear span, and I designed that. It was built in '88, and we weren't calling it mass timber back then. But today, because of the advent of CLT, another tool in our tool bag, we're talking about mass timber a lot. And it's lightweight, prefabricated components and environmental advantages. They're, of course, zooming it to the top of the list. And we all have seen these pictures before, and so I'll move through them quickly because it's not the primary focus of our topic today. But it does get us thinking about timber and help us understand why it is that timber is coming back in vogue. And Greg and I wrote this a guide to wood construction systems. It's one of the Wood Guide articles that you can get offline that we just talked about. And it was about trying to develop interest and show people how to work with timber in a new way, as you can see in these big, large buildings that are coming about today. We just developed a new test apparatus. You might have followed me on LinkedIn for designing ways of understanding the minor and major axis shear in major panel sizes, 10 by 40 foot long, for example, where we have point loads. And we know intuitively that shear is not even though it's 3/2 VA, it's really a width and length issue, horizontal shear. And so we know that, and we know mass timber panels have better shear properties in their full size than they do in small confounded samples that are used to test for most of our code submittals. And some of the things we're doing at the lab is opening up this can to understand it in a better way, in a way that helps us deal with our timber structures differently. And timber has that aesthetic appeal and its warmth and its qualities, aside from its carbon footprint, that are bringing it into play. And back in 1972, 73, 74, 75, when I began to start my career in timber bridges and buildings, we still had a tremendous interest in timber bridges. And over a period of 4 or 5 decades, that timber bridge interest tended to wane as people moved away from concrete and steel. Away from timber to concrete and steel. And I can remember people telling me when I graduated, timber bridges are probably not in vogue as much because they don't last a long time. They, they don't carry loads a great distance, so they're higher maintenance costs. And we began to hear this story, and we were told that steel and concrete bridges were going to last a long time, 100 years. But one of the bridges that I finished designing here just a couple of years back that's netted us 4 or 5 major awards is this bridge right here called the Roger Bacon Bridge. And you can see the bridge below that it replaced, that's steel. And the age of that steel bridge is 48 years. They couldn't keep it sandblasted and painted enough to keep it in service. And so the owners went to a new bridge, and this time they chose timber with the longevity that they were looking for, as you can see here. And the result of that timber bridge was minus 960 metric tons of carbon embodied minus versus 2,760 plus carbon tons in the steel comparable. And so that netted us some of these awards as people today are becoming very, very interested in about carbon. And I thought, just to start off, to get us thinking today, I'd put you down and show you my top 10 bridge restoration projects in Australia. We've got an average age in Australia of 82 years in timber bridges. We've got some 42,000 timber bridges in terms of ped, highway, rail. And so there's a lot of timber bridges left in Australia, and there's not enough money printed in Australia if someone decides they're going to replace them all. So we've got to extend life. We've got to bring value to the communities, because a lot of these timber bridges are in the outback where there's not a lot of traffic. You've got 2 or 3 or 4 or 10 or 20 or 100 vehicles a day across the bridge. There's no money to put $10 million into a crossing. Furthermore, by law, they're required to do sink funds and allocate funds every year to replace that structure. And if it's carried on the books at $25,000 now, and you replace it for $10 million, guess what? That drives the ratepayers' tax base up, and people don't like that. So restoring timber projects timber bridges is a pretty important aspect. And here's my top 10. I'll just take a look at them for you. You probably have driven across one without even knowing it. South Arm in Brunswick Heads is a reclaimed hardwood 2-lane bridge that looked like this before and looked like this after, as we put it back in service for another 100 years and fixed it back up. A lot of reclaimed materials used in that process. Delegate River Bridge in New South Wales, Coomashire. You can see what it looked like here before and what it looked like after, as we kind of reinvigorated the bridge and put in new design strategies to get it up to speed for another 100 years. It was 90 some years old. Most of these bridges I'm going to show you are approaching 100, some of them over 100. This is a Toowoomba Rail Trail Bridge, which was 130 years old, which we designed a restoration for and put back into service as a light vehicular ped bridge. Elliott's up in North Burnett. As you can see here, this bridge on old kind of cast in place concrete structures. The bridge was due for replacement, but they had 2 ratepayers on the other side of this bridge. And there's just no way there was the money to do it. The new bridge was millions of dollars more than just restoring the old one, as you can see here in the new look. Sugarloaf, 130 years old in Victoria, southern Victoria. You can see before and after restoring this bridge back to service. After 130 years in service, we turn around and design a restoration for another 100 years. There's no use-by date for timber bridges. Oftentimes we hear people say, well, timber bridge only lasts 40 years. Well, that's odd. The average age of a timber bridge in Australia is 82 years old. Well, how is it they only last 40 years? There isn't a use-by date. There's no code today in the world that says timber bridges only last 40 years. People need to chat it into me if you can find a reference. But there's just no such reference. Timber bridges are lasting a long time, and if properly designed and maintained, they'll go the distance. This one here in Queensland, Mountain Creek, before, after, restore the bridge, put it back in service to carry traffic. Barlows Gates and New England Highway, before, after, restoring it with a new glulam deck, a new glulam substructure system designed to go 100 years. Cowley Creek, before, a concrete bridge. This is after. This is a whole bridge being lifted into place, completely pre-assembled and dropped into place, 17-meter clear span. McFadden Bridge, take the old structure before and turn it into a new structure like this and save the community millions of dollars doing it. Running River Bridge, a long way from anywhere, in Charters Towers. 3 hours drive to Charters Towers, one of the few timber bridges they had left, down to 5-ton rating, and looked like this. And when it was done, it looked like this. So people didn't have a reroute. You could get a 44D across it. One of the big jobs that I do today is that I'm responsible for developing the compendium of maintenance practices for railway bridges for AREMA, American Railway Engineer Maintenance Away, Committee 10, and I'm the chair of that committee. And one of the great things about this committee that I like, along with the history of 40-some years that I have in this business of designing bridges, is the fact that I get a chance to see others bringing all of their maintenance issues to bear, and I can look at the pictures. And there's the pictures that I just want to show you a few of them. We often think that concrete is going to last 100 or 150 years. Well, anyone that's had a concrete bridge blow up on them in 30 to 40 years knows better, as you can see from these pictures. This is the same concrete that we're being told lasts 150 years or 100 years. And this is a picture here of the largest civil infrastructure disaster in Canada's history, Gardner Express Parkway, an average age of 32 years, concrete bridges, $1.8 billion to upgrade and replace. And this is a product that we were told was going to last 100 years. And so with that kind of concept, we see these concrete structures having their own issues. Well, people say, well, Dan, it's chlorides, or it's reactive aggregate, or it's not enough cover, or it's this, or it's that. Well, those are basically quality control issues, just like anything else. If I'm allowed the quality control that I need to put into a timber bridge to make sure that its maintenance costs are lower, its life is longer, timber bridges go the comparable distance. The Swiss Institute says that the average cost per year for maintenance of a timber bridge that's properly designed is about $450. The average cost for concrete that's properly designed is $956. So timber, when it's properly designed and built, can go the distance and compete with these types of bridges. No one wants this. So in the steel side, steel has its own longevity issues. Look, you can't keep it painted enough and blasted enough. You know, this is structural paint here over a rusted bottom. This is rust resistant steel. Close to the coast where there's a patina of salt water with chlorides, this is rust resistant steel at 18 years. This guy at 48 years looking like this. No one wants this failure. So timber bridges can last a long time if constructed properly. The guy on the left, 200 years, no nails, not a single nail. The guy on the right, nearly 500 years old or better. Guess what? They're built to last. Since the beginning of time, really, we've been using timber from felled logs across the river to Caesar's Rhine bridges. Timber bridges have been around a long time, lasting a long time. This is a leaf spring bridge. And you can see why it's called a leaf spring bridge. And this is here. Very old, lasting a long time. This bridge here in northern India is made of Fiscus benjamina. They grew this bridge 500 and almost 600 years old in a tropical zone. And they got a single lane and liked it so much that they grew a double decker. And these bridges are 600 plus years old. They grew their handrails. And why is it that they lasted this long? It's because they grew their connectors. See, it's often in the details that we have our problems with timber bridges, the devil's in them. And so this bridge at 55 years old was going to be $24 million to replace this interchange, Keystone Wise near Mount Rushmore. And the owners came to us and said, well, that's a lot of money and people don't want to take it down. It's iconic. And we said, well, let's inspect it. When we inspected it, the only thing we could find bad with it was the concrete and 3 little bad actors in timber. And we restored it with high strength fiber, as you can see here, extended its life another 100 years, put a new timber deck on. This bridge was 55 years old and the concrete deck had been replaced 3 times. Finally, they went back to timber. So greenfield bridges are also coming to play in this last 30 years, 40 years, as we consider better carbon footprints and better longevity. As you can see here, reinforced bridges doing the job of carrying heavy vehicular traffic. This one here in Austria, where it's on the Roman road. I designed this bridge and they liked it so much they built 6 of these bridges. This one I designed in Hokkaido, Japan, called the Bridge of 1,000 Trees. It's a meter depth limitation because of a waterway. This is a heavy duty truck bridge, 40-meter clear span. And this has been in service for 27 years. I designed this back in the early 90s. So the key reasons the number of timber bridge being designed and constructed is increasing is because of cost savings. Traditionally speaking, timber ranges in greenfield somewhere in the 50 to 70% of the cost of steel. Once you get over a 25-meter, 30-meter clear span, concrete's own dead weight is its killer. When you're getting to 35 to 40-meter, concrete is just not in the running, even though they continue to use it to cross the Bruce in Queensland. Even though it's not cost economical, they do. Why? Because they don't understand timber. They haven't been trained in timber. They've been trained in concrete and steel, and engineers tend to be in-aligned conservative thinkers, and they don't want to deal with things they don't understand. And they see timber in terms of high maintenance costs because that's what they've dealt with timber bridges that have been improperly maintained and built many years ago. This carbon and environmentally friendly sequestering of carbon credits is a critical aspect of the reasons for the growth in timber bridges today. Ease of construction, reduced cost of maintenance, silica fouling and contamination that it doesn't have, energy efficiency, longevity. So bridges can be built to last if they're properly maintained and inspected. Extending the life of our timber bridge assets and building timber bridges is the way forward. Governments struggle with an aging inventory of timber bridges. As I said earlier, the average age, 82 years. So governments are looking for ways to be able to extend life and keep costs to a minimum. When you look at these lifetimes of decks, superstructure, and substructure, you can see why governments and maintenance people have turned out and turned down on timber bridges. It's because the techniques they're practicing are shortening the life of their timber bridges, not extending the life. When you drive vertical spikes through a deck, you shorten its life by 66%. So 15 years is its average age because of vertical spiking from the top. Water follows the spike trace down in, gets in the bright wood, and it decays. Superstructure girders held in place by vertical bolts that go all the way through the curbs, the deck, the girders, the corbels into the substructure. Those verticals let water into the middle of the girders and they just don't last. Substructure piles, the same thing. When you can turn this on its end and make your decks last 65 years, your super last 75, and your substructure last 100, then things change. And that's what we're talking about today. This is the other part of that equation. This is the cost structure. When you look at concrete and these per square meter cost, this is with 25 to 35 meter clear span. If you start to take concrete out of 35 to 40, these numbers even creep higher. If you put steel girders underneath it and put a concrete deck, it's the same. So when you look at restoration, for example, an extension of life, or greenfield timber with this number, you can see why timbers come into play. So these are some of the key reasons: environmental, longevity, floodplain and heritage consideration, carbon trading, cost benefits, reduced site impact, smaller work site footprint, less impact on vegetation, simpler site management. These are key reasons for restoring and extending life of the existing bridge inventory. Reduced atmospheric impacts, for example, from cement dust and silica. Reduced community impacts, less need for heavy transport involved, and less impact on local traffic through long-term reroutes and bypasses that are there for months on end while they're building new bridges. And longevity, of course, is a key reason. Floodplain issues, the 1 in 100. The old days, we used to see them build their log girder bridges low so that when the floods went by, it topped, it went clean over them. If you're going to be a bear, you want to be a grizzly, you're going to stay low or go high. So if you've got to replace all your bridges and come into new code requirements, they all got to be high. So that drives approach cost and all other costs with it through the roof. And of course, heritage considerations. It's Kerwin's Bridge in Victoria. People just don't want them torn down. People get attached to their old timber bridges, and then heritage considerations become big. And of course, as I said, carbon, 22 times less energy than steel and 16 times less energy than concrete for an equivalent load capacity bridge. And it removes CO2 from the atmosphere because our forest, of course, through photosynthesis, sequester carbon so that it can be embedded and stay in these old timber bridges. So part of this in the greenfield, this extension of life and longevity, is the idea of pre-machining, pre-assembly, post-treating, test fit, and take on site and treat them like Legos and install them so quickly, reduce site time. As you can see here, this bridge I just inspected recently was in Canada, that because I'm senior global engineer for all of our different divisions for WRD. So I oversight all the different areas around the world. As you can see, this one here, 22 meters, as it sits here, 600,000. This one here, 35 meters, completely pre-assembled, this clear span, 62.5 ton, 2-lane traffic. I just inspected it today. It's been in service now a year or two. Doing a great job with slip distortion resistant FEMs, fixed end moments, allowing us to assemble on site, install lightweight cranes to put it in place. So we teach these courses around the world about how to do things with timber. And one of the big ones, of course, is our level 1, 2, and 3 on life extension for timber bridges. As you can see here, the guy standing in front of a 100-year-old timber covered bridge. So the resurgence of timber structures. Rapid installation. This is one of the big ones today that we see as the reason for bringing timber structures back to play. They're lightweight. they minimize interruptions to traffic, and they reduce labor costs. This bridge here, Boundary Creek, just outside of Brisbane, we had 2 days from 7 p.m. on a Friday night to 8 p.m. on a Sunday night. We had to basically take a bridge out and put a new one in. And that's what we did by pre-assembling, getting ready with a crane. And this one section, 2-meter wide sidewalk, 2-lane, weighed less than one precast concrete girder of the same span, the same capacity, that was lifted into place by that crane the week before. So timber and its lightweight nature make it easy to lift into place and provide for, basically low initial cost. And its self-weight, being 1/8 the dead weight of concrete, 1/5 the dead weight of steel, allows designers to be able to consider and reuse old existing abutments, again saving money and extending life. So this is the carbon check. This is a few key bridges I brought into play, but you can see them here, minus 980 on this bridge in carbon. I mean, these are big values when you're thinking about carbon considerations. The wood has its natural resistance to chemicals too, that's important. Like when you put salt on the roads in some countries for winter conditions, that's good for wood. If you got different chemicals, if you're by the ocean, that's good for wood. And because wood likes the salt, it neutralizes the pH wave of acidic enzymes that are caused by decay hazards. This exposed corrosion, you can see here, look at the highest zones in Australia for exposed corrosions. Wood likes exposed corrosion zones, steel doesn't. You can see this bridge here was in a high exposed corrosion zone, and here's looking at the steel in the embedded side. This is steel exposed and embedded. You can see the difference in how it was impacted by salt. Look at this one, 15-millimeter diameter stitching bolt had ditched off to that thickness because of embedded corrosion, exposed corrosion. Exposed corrosion, exposed corrosion. Fatigue resistance. Wood is not negatively affected by fatigue. It likes repeated loads. It doesn't fatigue easily. And that's an important aspect of timber bridges. Fire resistance. We always hear about wood, oh no, fire. Well, really what goes on in fire is the timber, the big dimension timber chars. The places where timber bridges are subject to fire is where there's decay. Because in that decayed wood, ignition point is dropped, that temperature is dropped, it ignites. Secondly, where all the verticals are, that's where the decay has gotten in there because of allowance of water in. And the fraise, that what engineers often call dry rot, which is a misnomer, there's no such thing as dry rot, that's what's burning here in these bridges. So fire resistance ratings are really about decay ratings. And that's how we use it. Wood is a great insulator. And so, as you know, if we want to embed steel fasteners in high-rise vertical structures, we get them inside the wood because wood is an insulator to keep the heat from getting at the steel and expanding it. And we can also use intermittence to keep wood from burning. If we want to keep away the fire potential from piles, for example, we can use intermittence. Another aspect of the new timber bridge growth is the fiber, high-strength fiber reinforcement of timber. As you can see here, long lengths of RP, reinforced polymer, 5 times the strength of steel at 1/5 the dead weight, strategically positioned in the bridge to enhance capacity. In this beam, we're applying RP to the bottom face, the tension face, and this beam, with one piece of reinforcement that's 70 thousandths of an inch thick, is doubled in capacity, as you can see it here. So this again has changed the dynamics of how timber plays a role. These curved beams are reinforced in strategic positions where the moment's a maximum and the extreme stresses are high. RP is applied for both vertical and horizontal structures. In the wood guide that Greg and I wrote about, I talk about this in the case studies at the end. So these codes that are used today in Canada and around the world, in Australia and United States, these codes represent the way they tell engineers how to design with timber. AS 1720, for example, tells people how to design with timber. And then AS 5100 stands between the timber code and the site and talks to engineers about how to design timber bridges. And AS 3660 talks about termite protection and so on. So there are codes and standards that are printed today that allow our engineers to be able to understand how to design bridges, and grading agencies that tell them how to choose wood. And grading agencies are set up to help sawmills grade the lumber and the logs, for example, so that then engineers can design bridges, specify a grade, and we use it. So in a dimension timber piece, typically the big knots are in the compression side. So girders, dimension timber girders have an upside down. I didn't know that. No one taught me that when I went through school. So there's a bigger knot allowance on the compression side than on the tension side. So this resurgence of timber structures is based on a lot of different things that we've talked about, all the way down to aesthetics. The susceptibility to decay is one of the key elements that people get in a concern or a panic about with timber. People say, well, Dan, this is going to decay. I look at my sidewalk and it's concrete, it isn't decayed. I look at a timber bridge and I get decayed deck planks at 15 years. What's going on? Why are you saying we can make this timber bridge last 100 years? Well, the reason is in the details. The devil's in the details. And if we design our bridges properly, decay won't be nearly the concern for the bridge that it is today in many of our timber bridges in Australia. Decay can easily be presented through careful design, chemical preservatives, and ongoing proper maintenance. So in this decay is this thing called a fungus. And how does it grow? Well, it needs things to grow. A temperature between 5 and 35, moisture over 22, oxygen greater than 21. Take away any one of those three things, wood will not decay. And if you make it treated, you make the wood inedible so that it doesn't decay because it's inedible. So there's two types of rots out there today, brown rot and white rot. Brown rot basically eats the cellulose fibers, leaving the lignin. The white rot eats the lignin first, leaving the cellulose, thus brown and white. You can see the hyphae growing here from a spore. So if I got this timber bridge that's from Queensland Plantation up in Queensland, and I'm letting all kinds of vegetation growth around those logs, it's holding moisture. The moisture's in there. I got vertical bolts in here. It's letting moisture in the middle. Vertical bolts here. Guess what? They're decayed. That foundation abutment is gone because it decays and goes away. Well, that's not wood's fault. We're putting verticals in it to allow decay to take place so that this fruiting body can grow. So if I take a spore, it grows a hyphae. It has a foot on the end of it, secretes an enzyme. The enzyme breaks the wood down. It's a cycle of life. We just don't like that cycle in our timber bridges. So we have to do things as engineers and designers to prevent this activity from occurring, this fungal colony from jumping our timber. This is a treated ironbark piece from Victoria with a bolt in it, 8 years old, and here's fungal fruiting bodies growing from it because we've chosen verticals to come from the top inside the bright zone. A lot of our timbers in Australia have natural resistance to decay. They're naturally durable. And so what isn't normally durable is that sapwood. The heartwood is naturally durable. And we have examples of in-ground durability, as you can see here. And then we have above ground durability. So our different species have different durability ratings. So it's important for engineers to look at the durability when they're designing their timbers. This is the decay hazard zone here. You can see the worst part of this decay hazard zone right up in here where we get lots of moisture, and that's the worst area in all of Australia for decay growth, what we call the decay hazard days each year. Because of verticals, we let more moisture into the middle, and even though the annulus is good here because it's got evaporated moisture. Inside here, where that moisture content hits 22% and it's not treated, it can decay. So horizontal connections, pre-machining, pre-assembly, post-treatment do away with this issue because we're not putting stuff in the wood after treatment. The old days, when I grew up in Canada, the bridge designers, you know what they did? They put their howe trusses in a building. They put a roof and a sidewall over them and kept the moisture off the joints. And that caused these old timber bridges to last hundreds of years in all environments. The other way we do this is we can use oil-based preservatives like penta and copper naphthenate to fix against cell walls, and we can treat them after machining because they're oil-based. They don't swell the wood up. And these oil-based treatments are what's recommended and used. AREMA, for example, the American Railway, they don't allow you to use water-based preservatives because they don't want the water preservatives to leach back out, and they want you to be able to machine prior to treatment. So you can see here, this is a typical incising piece. This is in a river. You can see this cant wood. There's no boxed in heart here. You can see the treatment all the way around here with incising. People think, well, incising is about injecting treatment into wood. Well, it isn't. It's opening up end grain. Incising opens up end grain, and end grain travel of preservatives 100 times faster than side. And so we open up a bunch of end grain, and the wood, the piece picks up more treatment. It goes deeper, and this gives us better performance. This is CCA treated in Castlereagh Coast, a hex log. They charge you more money to treat a hex log because it's harder to get the treatment in to 0.2 kilograms a cubic meter, because they've sized off all the sapwood. They cut it off. So it's harder to treat it. They charge you more money for it. And here's the CCA basically leaching back out of the piece from a deck, the ply deck, and this hex log. Double Canadian cut, 6 sides. That's why they call it a hex log. And so this is not working. Who wants the CCA in the drinking water? And this is what happens when you treat stuff and it leaches out, and this is a sapwood. It's gone. So I've walnut shell blasted it and garnet shell blasted it off, and you can see where the decay was. It was eating away at the softer tissues in the wood and taking the sapwood away, as you can see here and here. So the surface life of heartwood is fully protected 50 years, you can see here. When you combine this with great detailing and understanding how to keep your bridge dry, you're going to extend life. The average moisture content in a timber bridge under a closed deck is 14.2%. Under an open deck is 16.4%. And 22 is the threshold for decay, 22 to 24. Why is it that 82% of all timber bridge degradation is decay related? It's because of connectors. It's what we're doing to our bridges. This Cowley log in Western Australia is very poor decay resistance, but yet it's been under the ground 10,000 to 50,000 years. This guy's standing on it, not decayed. What was missing? Oxygen. So timber has this natural durability, and it has this impact from having the right ingredients of moisture, of oxygen, and temperature. And when it begins to decay, these things are impacted. It's color, odor, weight, strength, and these are the things that get impacted. In addition to decay, we have insects and worms. And you can see here, this is down the Gold Coast. This one flushed out here recently. This is not a good place to be inspecting a bridge. So there's a termite hazard zone here in Australia, where you can see the highest is D here. And so we have to watch our timber bridges for termites too. I mean, this is another big factor that we have to guard against. White ants. You can see white ant trails here. So this is a treatment, pentachlorophenol incised, set beside a termite colony, year 1, year 2, year 3. So when we're properly protecting our timber bridges, they're standing the test of time against these types of approaches. Marine borers, another one called shipworms or teredo. You know, they get into our pieces. Well, you can see this concrete block with sand. That keeps the marine borer. It's a crustacean that augers into our timber pile, then sieves organics from the water, and we don't like our piles being made into Swiss cheese. So we put this with sand there so the pile can shrink and expand. Or you can use high strength fibers. And again, there's a marine borer hazard zone. As you can see here, the highest up in, again, northern Queensland, the most hazardous. So these marine borers are another part of what goes on. Well, we worry about crustaceans on on wood. We really don't worry about them there, but here we have them on concrete on Bribie Island, and it's impacting strength. Why? Because again, concrete can get impacted by different things than timber. People put Denso cloth, never do this. This just leaves a chance for more decay. Moisture content runs up higher in the piece, and the marine borers didn't get you, decay did. So there's better ways to do this that we'll talk about. I like to just take a note to say that Castlereagh Coast, that's a big shire up in northern Queensland, in the highest decay hazard zone, highest marine borer hazard zone, highest embedded and exposed corrosion zone in the country. All those worst termite zone, highest zone, they've restored 38 timber bridges over the last 12 years and built new greenfield ones. In these highest decay zones, they're turning back to timber, as you can see here in this one here. 279,000 versus 3 million. It's about money. So lots of different physical agents impact our bridges, as you can see here. debris fields, impact, verticals, impact here, vertical spiking. You know, this lateral load here gets at our girder and corbel and pushes it off from floods. Undermining through stream migration that undermines the side, pulls the whole abutment over. These are decay prone areas. If you wanted to Google and pick this up, shows you what we do today and why it's so poor. All these vertical fasteners creating spots where there's high MC and leading to decay. This cribbing, vertical fastener in treated wood, first thing you know, it loses compression perp. As little as a 10% loss in specific gravity due to decay leads to a 65% loss in shear, 70 in bending, 75%, and 80% compression perp. And this is compression bulging, as you can see here, leading to a settlement of the road, all because an engineer didn't understand about vertical spiking from the top, letting moisture into the bright wood. Decking, vertical spiking degradation. This is up at Squatters Bridge in Victoria, 118, 70, some almost 140, 50 years old. What's left in this connector? The horizontal portion. What isn't left? The vertical portion. It's just that simple. Vertical. This guy here in New South Wales, beautiful concrete pier structure, puts a brand new bridge on it. All the verticals into it lead to decay around the verticals in the packers, the headers and girders. The first time it gets a lateral impact load, there's no resistance left anymore. They're all decayed. It's gone. 9 Mile Bridge is out. This isn't wood's fault. This isn't wood's fault. This isn't wood's fault. This isn't wood's fault. This is designer's fault. Even the mastics don't work. So vertical fasteners lead to degradation of the timber and ferric degradation. You can see here. Ferric degradation. That's ions, ferric ion embrittlement of the lignin, which opens up the wood around the fastener, letting more water in. This is Bolero Bridge in Coomashire. You can see they put new concrete deck planks on it because the timber ones weren't lasting. They put verticals right straight down through the girders, put meltoid barrier, which killed them, held the moisture in, and the whole bridge had to be replaced. You know, the girders were all ruined, and we replaced it in 11 days with penta-treated girders, put the new concrete deck back on it, wrapped the piles to create a better abutment vents and so on. This is down at Barwon Heads, where they wanted to have drains in their deck because there was water ponding. And so they sent them out to put drains at 20 feet. The cross bearers were at 4-foot centers, and no one told them to start at 2 feet. And so they basically put a drain over top of the cross bearer. Within a year or two, the cross bearer started to grow a grassy hayfield, lost compression perp, and up top started a pothole. They sent them out again, and they put in 2 treated ironbark Kentwoods. And because they couldn't get it in, they had to use a shallower. So they put in a packer, put them in, squeezed it together. Another year went by. They basically seasoned. Another pothole formed up top. They had to go back, put in a second packer. And so 3 or 4 times they're back to the site. The asset manager saying, I can hardly wait to get rid of timber. It's a terrible material. I wished I hadn't built with it. I wish I didn't have these timber bridges to deal with. And the whole time, $2.49, they never bothered putting an extension on that drain to keep the water off it. So it's not timber's fault. And here, the same bridge, they didn't want the water to get on a galvanized pipe, so they put the extension on it, but left it off every place there was a timber. See, that's not wood's fault. And tight the kickboard, kept it tight to the bottom, no drainage. You put it tight here, it decays. Open it up, it doesn't. This is the typical way things get done. Victoria, Violet, and here you see an engineer's called in. Here's a crack forming on the front of the bridge. You can see the ruler here, and they're asked what to do, and the engineer comes in. He does bore sounding. You know, what's bore sounding do? You just drill a bunch more holes and let more termites in, when you can use non-destructive testing using drilling holes. So he says, okay, well, these piles must be settling. They're almost 100 years old, and they must be settling all of a sudden. So I guess I'll wrap them with a concrete wrap. I'll put a steel cage. I'll use a polyester zipper wrap, put in dry mixed concrete. Capillary action brings water up in the pile. It swells, bursts the concrete. He has to go back. Gee, I got to fix this. This time he's gone back. He puts new concrete piles in place, and he puts web stiffeners in some locations and not in others. And he's still trying to fix the bridge. They're at 285,000 now, and the bridge still is settling. He doesn't know what's going on. And at no time, nobody runs a set level upstairs to see that the new cross bears have shrunk. And you can see here with the clips on top of the composite eyes, and there's a space. If someone had just walked up the bank and looked at this space, they'd have recognized that that's what caused that. You see, we've got to think about timber in a different way. We've got to think about it in terms of advanced inspection methods. Look for these bad actors that are laying on the bank, not the guys you can see quickly. They're easy to do. But these guys, the ones that are just underneath the surface, these ones, the cavities, like this one. We've drilled, bore sounded here, left it in the middle. There's a vertical bolt down through here. It's causing the cavity. We find it with non-destructive testing before the bridge fails. That's Lori with his head up inside it, because we're able to moisture content test these pieces, use a stress wave timer, find these bad actors, looking inside here and here, and here's what weird caused it. That's the vertical, that's the bottom, and that's what it looked like. And so if we're not using inspection techniques that help us find these bad actors and know how to fix them and not design the same way again, then our timber bridges become a burden to our communities. Bore sounding's the old way. This is bore sounding on steroids. You just keep drilling holes in it. You know, it was good in 1900 when labor was cheap. We didn't care how many times we replaced a girder, but that doesn't work today. And where are we drilling? Where we put the verticals. And we put the vertical and it splits it. So what do? We put an anti-splitter bolt in, and then it splits it in 4 ways. And so we're drilling more holes. 10 years ago, when we drilled the first one and found a cavity, we put a white mark. We just kept on drilling them. And because the bores, the auger bits stuck in the wood, we started drilling with bigger holes because they don't get stuck as much, big ones. And so, and there it is, you put a bait box beside this 15 millimeter hole and a 20 millimeter hole, when 10 years ago it was a 230 by 230 pipe diameter, and Gap's sitting down here to himself, thinking to himself, is that the termite going to go in that bait box when he could have went in that hole? No. So these combination of events with vertical spiking and poor inspection techniques have really led to problems. When we can use non-destructive testing like this one to find bad actors, calibrate these bad actors, find these guys before they find us so that they don't end up like this. This was outside of Brisbane. We're going to put a new precast concrete on the old timber piles. We just drill holes in them and found nothing going on. So we let them go. Well, there's cavities in there. And that's what happens when you miss it. So we could be investigating in piles, for example. This one, we were here in this community, and the guy said, look, you know, this bridge was built in 1922. And I said, well, what do you mean? He said, well, you can XXII. And I said, well, look over that pile. It's got XI on it. It must have been a long time building that bridge. That isn't the date the bridge was built. That's a depth shield. That tells you how far to the tip. The great pile drivers of the past would put the depth on it so we could rate a bridge. If I don't have geo and I don't have depth and I don't have species, how do I rate a bridge? So rating bridges is pretty important. Looking at depth shields, and when I can't find them, use a pulse echo technology device that I can send a signal down these sill piles here and figure out how deep they are. I know the species, I know the taper, I know the geo. I can then figure out what my capacity is. Use times of flight to be able to get my capacity for existing pile banks and then reuse them. Don't put micro piles in. Piles are as good as gold down below oxygen. You get down 300 millimeters, piles as good as the day it was driven. And so we can reuse our piles. And, you know, people come out of school today and they're trying to identify splits and checks in wood, and they call them horizontal shear checks. Well, this is a horizontal shear check. 60% of all horizontal shear is late wood, early wood interface. This is the shear check or crack. This is the shrinkage check. What's the difference? Well, that's the tree just cut down. He's cracking along the ray lines. Why? Because he's shrinking and it's leading to checks that are naturally occurring. This is a horizontal shear crack. And so that isn't a shear crack. So if I'm calling this shear cracks, it's not a shear crack. This is a bridge called Running River, where they did everything wrong they could. They encased it in concrete, spiked the approach sheeting planks, each one of them to the pile, which you don't do. You let them settle on one another. You had piles that were braided at the top, completely cavitated. They put these T's underneath them, and the top bolt picks off 80% of the load, and then it cleaves. And the whole thing was a mess. And, back in 1900, the biggest lateral load was from debris field. It wasn't a Model T Ford. Most of these bridges at the turn of the century in 1900 were designed for 12 tons. And so you can see this was 1922, it was 22 feet from the depth shield down. And so both of these laterals are turned one way. It doesn't do much for nosing loads from the wheel. So turn one of them. And so that's fixing it. Cut the piles off below Bright in the water, put these pre-assembled, pre-machined, post-treated vents in there, swivel lift buckets, a new penta deck transverse vertically laminated, 100-year design life, and put that bridge back in service using the materials at hand and do it at a fraction of the cost of new. This is Newry Island, before and after. 400 ratepayers on this island, 35-ton piles, every one of the girders vertically spiked and ruined. And the steel uni bridge was millions of dollars. There was no money. And they asked me to come in and design a solution. And we put verticals and look at all these holes. Possums were living in them. And so I said, you got to put a new bridge top. And so we designed a new bridge with no verticals from the top, micro bat chambers. And here it is going here. This is salt water and a floating scaffolding. And we're in 11 days putting a new bridge on, as we see it here. So these bridges represent the future for Australia, using old and new, proper design details, advanced materials like shear panel, fixing the old, restoring with diffusers, upgrading, using Dutchman's patches to fix next down piles in ocean environments, 2 halves, diamond cut the penta piece in 2 halves, put it on the piece and Dutchman's patch, and look at this, don't change the whole pile out. Use new techniques that are going to extend life and get where we're going and do it profitably and economically, and then inject to restore in situ. So this is the summary that I leave you with the top 10 things that you can do to extend life in timber bridges. Change vertical through bolting to horizontal. Stop meltoid barriers. Don't have meltoid between wood layers. It traps moisture. Ensure positive drainage that gets water away from the wood. Ensure that your steel side plates are galvanized, and then use moisture content change, induced dimensional change, ovaling. Don't use bending. It doesn't work. Stop the use of near end drift pinning. Provide proper clearance and breathing for your timber elements. Stop the use of heavy percent solids. Don't put paint on things that are 29% solids or more. Stop the use of heavy notching. Use proper sized timbers for your piles or your caps. So that's the conclusion I have. And now I'd be willing to take some questions if we've got any.
Thank you, Dan. That was an excellent presentation. I certainly took a lot from that.
What was my time there? I wasn't watching my clock.
Oh no, you actually made perfect
over,
time.
not bad.
No, yeah, that was fantastic. I've got a couple of questions myself, but I'll ask a question from Jerry Howard first in the Q&A chat. So if you have any questions, just put them in the Q&A. Hi, Dan. I love those old timber bridges. And I'm wondering how they'll perform in expected higher flood events. You touched on that briefly with that that one where you were talking about how the flood was the primary lateral load, not the cars on top. Are you finding that increased flood risk is governing?
We have one that I'm just finishing designing for up Bananatyre right now. And, as you know, buoyancy force is equal to 1 minus the specific gravity times the volume. And so when you get hardwoods, they tend to have closer to 1 for a specific gravity. So they tend to have a better resistance to buoyancy. But what we're really doing with these bridges is we're designing for them to have the impact loads. If they're going to stay in harm's way, we're going to have a debris field allowance. We're going to have to design for a debris field for lateral load and impact. Or we pull the soffit of the bridge up over the ARI, 1 or 2. So it's a design feature. People say, well, timber bridges won't last in a flood. Well, that's because they've got old timber bridges with vertical fasteners where they're decayed around the vertical fastener. They have no end fixivity. They've lost it all. And they get hit with a debris field from a lateral load. The decays all around the retainer bolts. And so it just flows off the abutment. That's what's going on. When they're properly designed and built and connected, A flood's just like any other environmental load. It's designed to take it. It's about design, right? That's what it's all about.
I suppose that question may have been getting toward the point of asking, is that design changing? But I suppose that would be felt more in the codes, which is a slow to follow through than what you might be designing for.
Right.
It's amazing that not only the moisture control is like, it's one thing for it to be not appreciated in the nuance, but when you point out examples where it's treated, where the concrete or steel is treated carefully, but the timber is actively not treated carefully, where do you think that comes from?
Well, I think, people say to me, oh, Dan, have you ever designed a bridge that's not treated? And the answer is yes, and tons of them. That bridge I showed you on the Roman road in Austria, where they had me design 6 more of them. That bridge wasn't treated. And so what you do really, guys, lots of times you're using spruce, for example, in Europe, and it's not treatable. You're using certain types of wood like inland Doug firs, not treatable. Hardwoods, you have a hard time treating them. It's just hard to get the treatment in them because you can't get it in the side grade. There's a lot of tyloses and block pits. So people say, well, Dan, could you design one that's not treated? And I always use this analogy, and it's a really interesting one for you. There's an island off the coast of New York State called Treat Island, where they put timbers in these treatment areas where they treat them and test them over time to see how they stand the test of time. And they took a 6x4 that was treated and a 6x4 that wasn't, drove a spike in both of them, put them up on sawhorses and let them go. And neither of them outlasted the other. The one treated didn't outlast because of the vertical that exposed bright, and the one that wasn't treated didn't last either. So there's equal treatment time, equal longevity time for one treated, one not. The key for me is verticals. I tell my engineering students, do one thing. If you do one thing from hearing me talk today, stop the verticals that originate from the top. I don't care if your deck is even not treated, does not have to be treated. If your deck isn't treated, stop verticaling from the top. You'll extend life 3-fold. 3 times. Just stop the verticals. If you've got log girders, stop putting them on the seats at the abutments or the piers with vertical bolts that go straight down through the center of the girder. It doesn't work. It's proven it doesn't work. It's got decay in it. That's why they have fire problems.
Is it tempting from an install point of view? Like, where did that come from in the first place?
Where did the verticals? At the turn of the century, 1900, back in the day, men were cheap, wood was cheap, and it was easy just to put fell the logs where you got to. You got to the side of the river, you cut the trees down. The ones with high taper were driven in the sandy soil. The ones with the less taper were driven where there was no sand. You had to go deeper because you had displacement to give you capacity if you were in granular. And then the ones with good, clear, bigger bowls, they were cut. They used core bowls, which are cheaters, so that you could have different length logs. And they built a bridge across the river. That's how the gridiron of Australia was established 100, 200 years ago. That's how it worked. And when they did that, the men would basically put it together by drilling straight down through. And you can see on their old concrete abutments, many of them without rebar, they have these channels down underneath the seat where you can go put the bolt on the nut on the bolt, and they're designed for verticals. And that kills them. We just know more today about what to do with timber bridges. I don't know what else to tell you. There's not many buggy whips built today. It used to be people died of appendicitis. They don't today. We just know more about what to do, and they're better design details. Lots of our state timber bridge maintenance manuals, design manuals, guys, Queensland, New South Wales, Victoria, not so much Western Australia. Theirs is pretty good. But you look at all these timber bridge maintenance manuals, they're in their 8th errata. They don't have timber bridges at the state level anymore. The councils and shires have their timber bridges. They're responsible for them. They go out to tender with these old 8th errata maintenance manuals, which are providing details that are antiquated and not right. They just need a change. They're screwing over their timber bridge assets. And asset managers are trying to struggle. How do I deal with my timber bridges? Because the way they're fixing them, according to these standards, actually reduces longevity. It shortens life. That's the problem right there.
Sounds like a lot of policy work has to be done there to change that.
Is. It's policy work, yeah.
Well, we're just over past 12. There are a few more questions. So I think that's all we have time for. But I'd like to thank you personally. I've got a lot out of that, and I think everyone else did too. So thank you so much. Just before we go, I will share my screen. Cool. So the next webinar in the WoodSolutions webinar series is on Tuesday, the 12th of July at 11 a.m. on designing to meet budget, how to specify the right timber products for cost efficiency by Lawrence Ritchie. So please tune into that. And again, I'd like to remind everyone that the entries for the Timber Design Awards are open and closing soon, so please get them in. We also are looking for interest in the Australian Mass Timber Full-Scale Test program. And that concludes our webinar. So thank you very much for coming. Thank you very much, Dan, for being here, and we'll see you in the next webinar. Ciao.
Thank you.